what's going on, everybody? It's Mr. Gus, and I'm back in the physics classroom where today we're discussing the differences between impulse or change in momentum and the conservation of momentum. We've talked a little bit about conservation of energy and work and the differences there, how an outside force on a system will cause a change in energy or work to be done on a system. And but also, we can redefine our system. We can choose an appropriate system in which there are no outside forces, and so work isn't actually done. Well, the same thing happens here. Let's talk about what we've been studying. What we have been studying are instances where collisions happen, and we're observing one object. So the demonstration we're going to have today are these two carts. And I've got the carts over here on the table. And so first things first, I want to think about the red cart as my system. If the red cart is my system and I give it a push and it has an initial velocity, we can see that the red cart clearly slows down when it contacts the blue cart, and we can explain why using impulse. If I have my two-cart system, the blue cart, let's label it B, and the red cart, which is much more massive, we'll label it R, is moving with an initial velocity to begin with, and then it collides. After the collision, we might call that red. We'll say it's a smaller final velocity, and the blue car is moving here. This is the before and after the collision. This would be our change in momentum area. We can study how the mass and change in velocity are related to the change in momentum. But if we wanted to look more closely, say, I don't know, at the actual collision itself, we'd say here's the red car, here's the blue car, and in this collision, there is an outside force from the blue car back on the red car, and likewise, there's a force from the red car pushing forward onto the blue car. If I was thinking about just the red car as my system, we would say there is in fact a change in momentum on the red car. There is in fact an outside force. What outside force is that? It is this force. It's the blue force pushing back on the red force, and because we have this outside force, we would say there is an impulse. Again, impulse is an outside force that acts during a time interval. We have the time interval of the collision. We have the force from the blue car on the red car, and this would be a change in momentum. That's why we see a change in momentum. That's why we see a decrease in the velocity. Now, this is because our system is just the red car. Let's re-envision this. If we re-envision this and say before the collision we have our red car moving at its initial velocity, and we have our blue car sitting at rest, initial velocity is 0, and then we have our collision, and after the collision, this red car is moving with a slower final velocity, and the blue car is moving with some new final velocity. This here would be considered, if I go ahead and look at the entire system as the blue and red car, and I think about the collision itself, I think about this red and blue car collision. If I think about this collision and the forces that take place, is there an outside force? Well, I know the blue car pushes on the red car, and I know that the red car pushes back on the blue car, but are there any forces outside of the red and blue car system that might cause there to be a change in momentum of both cars added together? The answer is no. There's no third force acting outside, no like hand or friction or whatever pushing on these cars. So in this case, there is no change in momentum. There's a transfer in momentum from the red car to the blue car, but within my system, the red, blue car system, there is no outside force. I would then rely on my understanding of conservation of momentum. And what that means is there is some amount of initial momentum up here. There is some amount of final momentum down here, and both of these, initial momentum and final momentum, are equal. This is the definition of conservation of momentum. With no outside force on my system, the initial total momentum of the system is equal to the final total momentum of the system. This is the general idea. This is the idea that I can select an appropriate system, in which case I don't need to rely on impulse. I can rely on conservation. This works especially well if I have no idea what this contact force is between red and blue car. there is a force, but if I don't know the value and I can't find the value, I don't have the tools to find the value, I'm not going to be able to use impulse to understand the momentum and changes the momentum of the red or blue car. So I use this when I have no idea what this contact force is. Now, there are 3 different kinds of collisions that we might consider, right? Or maybe 4, but there's a couple different kinds of collisions that we can consider, and let's look at them. The first one is called a perfectly inelastic collision. This is when 2 objects collide and stick together. Let's go ahead and check this out. I've got the red car here. I've got the blue car here at rest, okay? And because they're at rest, I'm going to slide this red car and give it an initial velocity, and we see that they stick together and become one object. We tend to call this a 100% perfectly inelastic collision, meaning that the cars become one object. There's no bouncing whatsoever. The cars don't bounce and stick off. They collide and stick together. We call this an inelastic collision, or a perfectly inelastic collision. This is where one object sticks to another after the collision. And mathematically, we consider the momentum of the initial car, let's say car red, plus the momentum of car B initially is equal to the momentum of car red B. This is just a general statement, but I know initially the blue was not moving. I can call that 0. I can say this is the mass of the red car times the initial velocity of the red car, because that's the equation for momentum. This is going to end up being equal to the mass of the red car plus the mass of the blue car times the final velocity of that red-blue system. I can add the masses together and multiply them by the common velocity that they will have. This is a general statement for perfectly inelastic collisions. Okay, and it's just based on I have my momentum initially for both objects, and finally for both objects, this is how it shakes out algebraically. The second kind of collision I have is known as an elastic collision. And we're going to talk about 2 types of elastic collisions, but here is one. One of the elastic collisions mean that things bounce off each other. They don't just stick, it's actually quite the opposite. They will come towards each other and they will bounce off one another. So let's go ahead and see what this might look like. I've got one object, blue car staying still, red car, which is much more massive, comes and they bounce off each other. They're going in the same direction, they don't stick, there's clearly a bounce, they end up going the same direction, but they do not have the same final velocity. There was some amount of bounce there. We call that bouncing, we call that an elastic collision. Or bouncing. It doesn't mean they bounce off and go opposite directions, it just means there's some amount of bounce. And so if I think about this, I've got the momentum of the red car initially plus the momentum of the blue car. And the blue car could be moving. I could slide them towards each other, it doesn't matter, but in this example, I'm holding it steady. Eventually, this will, and this is the initial, eventually this will equal after the collision, the final momentum of the red car and the final momentum of the blue car. And I can go ahead and substitute in their more specific variables. So I've got mass of the red car times the initial velocity of the red car plus the mass of the blue car times the initial velocity of the blue car, which is 0. I can lose that in this exact scenario, but not always. Is going to be equal to the mass of the red car times the final velocity of the red car plus the mass of the blue car times the final velocity of the blue car. This is a general statement that I can use for these types of semi-elastic or semi-inelastic collisions. There's a bouncing, there's not a sticking, but there's a bouncing. Now, the weird thing about this is that the elastic collision is not perfectly elastic. In order for something to be perfectly elastic, we have a caveat, we have a rule. If something is going to be perfectly elastic, 2 things need to happen. Two things. First thing is that momentum must be conserved. There must not be an outside force on it during the collision. The second thing is that kinetic energy needs to be conserved before and after. If they're perfectly elastic, there's actually no collision at all. There's no loss of energy to thermal energy, to sound energy. There's a collision that doesn't have a loss of energy. These types of collisions are rare and more theoretical than anything, but I'll show you my best example of one in a second. Perfectly elastic means that there is a conservation of kinetic energy in the collision. Can't actually collide, because if they actually touch, if they actually collide, we're going to hear the loss of kinetic energy or mechanical energy in terms of thermal and sound. So they're not actually going to collide. It's almost like I got to use some kind of magnets to apart. So that's what I'm going to show you right now. Is a general, as best as I can create in my classroom, a general, perfectly, quote-unquote, elastic collision. So I'll take this card, I'm going to point these two magnets in these cards at each other, and we see that they don't actually touch, right? They get close, and they push off. So let's see what happens here. I'm going to slide them towards each other. You don't hear the collision, do you? As these things slide towards each other, you don't hear the collision, but you see the blue car snapping off. You don't hear it, because if you heard it, it would sound something like this, and you'd hear the loss of energy. That sound is a loud sound that dissipates or removes mechanical energy from my system, but without it, let's see if I can get the red card to move. Ooh, that got too close. That's not going to work. Without, I got the red card to basically stop. Without the contact, though, we are much, 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 much closer to a perfectly elastic collision. In this case, we're going to have the same scenario as above, but, as a caveat, we have to also remember that the kinetic energy of the red car initially, plus the kinetic energy of the blue car initially, must be equal to the kinetic energy of the red car finally, and the kinetic energy of the blue car finally. This is the caveat. If something is perfectly elastic, this is also true. This statement is rarely true in collisions. Rarely. This is a theoretical idea. It's a way for us to check if a collision was elastic or inelastic, but it is not something I want us to say, hey, that is something that's true. This is not true. In our very first example of colliding cars, we disproved that this kinetic energy happens when objects collide and make a sound. So, I've got my perfectly inelastic collisions. I would say perfectly inelastic collisions, things collide, they stick, I end up with this equation. Elastic collisions, or sometimes called not perfectly inelastic collisions, or not perfectly elastic collisions, we have this like continuum of elasticity, right? There's less or more energy lost in the collision, and it slides towards elastic or inelastic. But when objects bounce off of each other, we fall into this middle category of momentum initially being equal to momentum finally. It doesn't matter if one object is stopped to begin with or if it's moving to begin with. As long as the two objects do not stick and stay stuck, we live in this middle world. Lastly, we have this very rare and perfectly elastic collision. If this is the case, then we know that the kinetic energy of both objects is conserved through the collision, which is a very rare case because we know collisions typically have sound, and therefore there's energy loss to thermal or sound energy. These are our types of collisions that we have, and this is how we can go ahead and use our conservation of momentum idea rather than relying on the impulse change in momentum theorem. If you got questions, drop it in the comments as always, or send me an email or ask me in class. Until next time, see ya!